All right, here we go. Let's take a look at the last section here. We're going to wrap up polar functions, which is pretty awesome. We're going to look at the rates of change of r. So we're going to look at the radius of these polar functions as it kind of goes around the circle. Let's start off with this example here. So we've got 6 sine 3 theta, and I love me some Desmos here. So I like to see these things graph. I think it's so fun. If you want to see this bad boy graph, so I went ahead and fired it up in there for us. So if you watch it go, yeah, I showed you the picture of it already. We know it's a rose. It goes out, it comes back, it circles back again. And then we start that retracing itself over and over again here. Holy cow, there it's finally done. So there's the shape, and how it's drawn is important. That's what we're looking at, is like the rate of change. So we're looking at, as I start to draw this thing, what's going on with the radius. So it's getting farther away, then it's coming back, it's going through, it's getting farther away from the pole, and then it comes back to the pole. So we're looking at that rate of change as I go around these different functions here. That's our whole goal. Should be a fun one. Let's check it out. So this one's not as cool. It's a little static here, but here's the rectangular version. Remember, this is theta down here on our x, and this is our r up here, our radius there, and we're going around. And I kind of want to take a look at the intervals here, what's happening. So let's look at the first interval, from 0 to pi over 6. So on my rectangular, from 0 to pi over 6 is this first chunk right here. So if you've got anything way to color code it, that kind of helps. What do you notice that's going on here? Well, 2 things I want to talk about. I want to talk about, hey, what is r? R is going to be positive, and what else? R is positive, and it's increasing. So I'm going to abbreviate with pos and inc because we're going to do so much of it. So see how this is positive? The values are between 0 and 6. So r is definitely positive, and then it's going uphill. So this first chunk, r is positive, and it's going uphill like that. Awesome. Then we're going to change gears, and what's happening from pi over 6 to pi over 3? Well, I'm going downhill, right? Here is whoop, comes back down here. So what is going on with r? R is still positive, and this is going to be important here. But what are the values doing? They're going down from 6 to 0, so they're decreasing values. So we can see him going downhill. And how does that relate to the graph? See how he comes back towards the pole or the origin like that. So we're kind of looking at the distance from the pole. Like, is he going away from it or coming back to it? Let's just keep this train rolling from pi over 3. So we're at pi over 3 here. He's going to go into the negative land, which is exciting, and down to here. So what's going on with r? Well, the main thing is he switched to negatives. And what happens here? He's getting more negative. So from 0 to negative 6, he's getting more negative. So he's still decreasing here. And that's this little part of the graph right there. Woo, exciting. Am I out of colors here? I guess I can go red. Red on red. Here we go. Then pi over 2 to the last chunk. So he's negative, but he's coming back to that 0. And I can see that he's coming back to that 0 like this. So we know r is still negative, except that now I'm actually increasing because I'm getting bigger. So I have something like this. So our goal here is to look at what's going on in these different intervals and figure out, hey, what is the distance from the pole or from the origin? So I'm going to kind of scroll down to that table, and let's figure out what's happening here. So on the first interval from 0 to pi, I was positive and increasing. Well, this is how it's written out. If r is positive and r is increasing, the function is increasing, what's happening? We say that it's increasing here. We say that that is an increasing distance from the pole. So this is, we're talking about the distance from the pole. So the distance, basically he's going away. So you're getting farther away. So maybe you want to write that in there too. So we're looking at the distance from the pole. Hey, you're getting farther away. Awesome. Excellent. So what about the next one? If he's positive and decreasing, so I'm still r is positive, but if the function is decreasing, I'm going down in value, well, what's happening? Just follow blue. It's also the distance is decreasing. So here you're getting closer to the pole or to the origin. We'll use both of those terms. Either one's cool. So here I'm getting closer to the distance is getting smaller, or the distance is decreasing. Excellent. Then follow it. If I'm a negative decreasing, so negative decreasing, so negative was this purple, I'm negative r and I'm decreasing. That's this one right here. Fill that in. We're getting farther away. The distance is getting farther. And then spoiler alert, last one, I came back to it in the red. What's going on here? That distance to the pole is decreasing. If you prefer getting farther away, if you like to use that, farther from the pole, and here I'm getting closer to the pole. So this table can help you remember, because this is going to be some questions. I'm going to ask you, hey, what's going on With r, is it getting in the distance from the pole, and the radius, it's getting farther from the pole. So we're going to talk about which way is it going as I build that thing. Awesome. That's really a good chunk of what we're doing today. So that's it graphically. You got a little table if you want. You can think about this or look at the image. What if, though, there is no picture? So I went ahead and said r is this function right here, and I gave you some selected values in this table. Can we figure out what's going on without the picture? Sure. Let's take a look at this. So I'm going to grab my highlighter. So the interval here is what? From 0 to pi over 2. So from 0 to pi over 2 is just this chunk. So we're looking at only this chunk right here. Let's talk about what's happening here. So tell me about r. So r is going to be what? I would say is r, first of all, is it positive or negative? It's going 0 to 5, so I would say r is positive. And what else about r? R is it increasing or decreasing? I'm going from 0 to 5, so I'm increasing. So we can use a table just as well as using the picture. When I have a positive that is increasing, what does that mean? So if r values are getting bigger, the function is increasing over that, I am getting farther away. So the distance to the pole, and you can use your table if you like, the distance from the pole is increasing. From the pole, he is increasing. So positives make sense, you know, getting farther away. It's kind of when you get into negatives and decreasing, it gets a little crazy here. So speaking of that, here we go. Let's take a look at pi. Oh, this one's not negative, but pi over 2 to pi. So let's just slide this over to here. Pi over 2 to pi. What's happening here? So now I've got this idea of what? R is still positive. So it's just still, the numbers are positive. I don't have any negatives here. And what do we know here? R is now decreasing. So we're going to say it's decreasing. When that happens, I have positive values that are going downhill. That means my distance is what? The distance from the pole is what? Decreasing. From pole is decreasing. Awesome. So you can use that little table. You can kind of think about what's going on. It's getting smaller and smaller and smaller. Awesome. What about the average rate of change? So I kind of gave myself some more space here. Over two areas here. I'm looking at the average rate of change between pi over 6, and I'll highlight those bad boys right here, between pi over 6 and pi over 3. So what's the average rate of change between these 2 points? Well, when I'm thinking average rate of change, I'm just thinking about what? I'm thinking about the slope of a line. So remember, old school, slope of a line is just y2 over minus y1. Remember this bad boy? And x2 minus x1. But what is this in polar coordinates? It's different now, isn't it? What is y? Well, it's like x and y, but we're now talking about r. We're talking about r2 minus r1 and theta 2 minus theta 1. But it's the same idea here. So that's pretty cool. So we're going to find the slope of the line. I went ahead and, spoiler alert, here's what the f of theta really is. Here's what r is. It's actually this circle right here, and this is the rectangular of it, because I wanted you to see visually what's happening here. So even without the picture, we don't need that picture. Let's do it with the table, and then we'll match it up what's going on. So if I'm going to find the rate of change, I'm going to say, pick either one, R1, R2. It doesn't matter. You get the same answer. I usually put the second one as R2. So I'm going to say what? On bottom is going to be my angle, so I'm going to say pi over 3. And then who's pi over 3's friend? Pi over 3's friend is 4.33. So that's my R2 and my theta 2. And then what is theta 1 is pi over 6. So I'm going to put this angle in. What does he make? Pi over 6 makes 2.5. Excellent. And I'm good to go there. So what did we find visually? So let's plot these points. Pi over 3 is about right here, and it makes 2.5. So here it is on the graph right here. And then pi over 6 is roughly there, and it comes up like this. So if we're finding the average rate of change, what are we doing? We're finding the slope of this line between those 2 points. So that's all it is. How much did it change? It's the slope of that line right there. Let's crunch some numbers. What is 4.33 minus 2.5? 1.83. You may have heard my calculator clicking. I want to double check I didn't make any mistakes. And then what do we do here to subtract these? If you want to get a common denominator here, you can. You can easily turn him into 6 if you double it, if you times it by 2. So common denominator would be 6. If you times him by 2, you got to times the top by 2. So what is 2 pi over 6 minus pi over 6? Just gives you pi over 6. Awesome. Then we're going to flip the second fraction and multiply. So really the top gets times by 6, and that's 10.98. And then the bottom stays pi like that. Or you can divide it all out in your calculator there. Eventually, this is a very calculator active section here. We eventually have to get rid of that and go to an approximate decimal here. I'd like to take it all the way down to one of these squiggly lines, approximately what. So we've gone as far as we can. So let's divide that bad boy by pi, or you could have done it earlier. As long as you get 3.495, we're cool. 3.495. And then what in the world is this? Oh my gosh, so what are we labeling here? So this is how the circle changes. So if we look at this circle, so let's go back to pi over 3 and pi over 6. Pi over 6 made 2.5. So pi over 6 is this line right here. Here's pi over 6. And it made 2.5. I can see it right there. Pi over 3 is this line out here. And what did it make? It made this dot over here. So we're talking about how does the radius change from this line to this line out here, this distance here. That's what we're talking about. So I don't know if this is in feet or miles or inches. I don't know what it's in. So we're going to say that it changes, the radius changes. I'll write this out the first time. Normally I don't write this radius part, but just so we're cool. The radius changes. What does it change? It changes 3.495 units. I don't know what we're in, so I'm just going to say units. And then that's going to be what? That's going to be per what? Radian. That's going to be what's on the bottom there, and that's our angle, and that's measured in radians. So we're changing 3.495 units from this line to this line over that time span. That's the average rate of change, and that's how we label it. Woo! That's a lot. All right, let's come on down here and take a look at part D here. Oh, this is a good one. We're going to estimate the value of the function at pi over 4. So let's go back up to our table and say, hey, where is pi over 4? Well, it's not on our table. Luckily, though, it's in this interval. If you think about the unit circle between pi over 6 and pi over 3, it's right here. It's pi over 4. I can see it right there. So it's not on there. We don't know what this function is. We don't have this table, but we can estimate this point right here. So I know if I take a look at this picture, where's pi over 4 in my picture? Well, there was pi over 6, pi over 3. Here's pi over 4 right here. And see how I have this nice blue line right there? We can use this blue line to estimate the black point on the line to get a ballpark idea of where the pi over 4 will be. Holy cow, let's do this. It's not too bad. So if I'm going to estimate this, luckily we know the average rate of change. So what did you find? Remember, you just found the slope of the line up here. So we're going to use our point slope form. Remember this bad boy? Y minus y1 equals m times x minus x1. So this is the easiest one to use because all we need is a point and a slope, hence the name point slope form, to write the equation of the blue line up here. So let's go ahead and pick a point and plug it in. So which point's easier to use? And this one, it doesn't really matter. If I have a 0, that's always a nice point to put in, or these are nice friendly numbers. But I can pick either point, the pi over 6, the pi over 3. I'll use pi over 6 because it's a little bit friendlier. So we know pi over 6 makes 2.5. Just want to double check. I'm cool there. So let's plug it in. We're going to say y minus the y value, which was what? 2.5, equals the slope, which we got up here. Holy cow, this 3.495. So that's the slope of the line, 3.495. And then we're going to go ahead and subtract x minus, what was our point for x? We said pi over 6. So we are using the point from the table. I wish that all fit on one screen here. I just want to make sure we're cool. We're using the pi over 6, so we had this interval. I'm going to pick one of the points of the interval, and my point I'm trying to estimate is in between, is somewhere in the interval here. So I'm going to pick this point. You could have definitely picked pi over 3. You'll get the same answer. That's coolio, but I picked pi over 6. Awesome. So I plugged that in there. Now it's just a matter of cleaning this up, and we're going to need some room to clean this up here. So let's go ahead and distribute this bad boy so we can kind of clean that up a little bit. So we're going to say y minus 2.5 is 3.495. And then that's going to be x, and then we're going to times it by pi over 6. So you're probably going to have to go to some calculator action here, and be careful with rounding. We'll try not to round too much. But what is that bad boy when I times it by pi over 6? So it should be 1.829. Awesome. So now let's just finish cleaning this up a little bit. What can I do? I can add the 2.5 to both sides. So I'll add 2.5, come over here and add 2.5. And those cancel out. And I've got this line here, 3.495x. And then if I add 2.5 to that, I'm going to get add 0.67 to it. So that is the equation of the blue line up there that I drew in earlier that goes through those 2 points right there. So that's the point. I'm sorry, that's the line through those 2 points. Excellent. So why did I do all that? Well, I want to know what is the estimated value. So that line's not perfectly hitting the curve, but it's a good estimate if I put pi over 4 in. So let's put that pi over 4 in and see what we get here. So I'm going to go ahead and plug in for x pi over 4 right here. And then I know the slope is 3.495. I'm going to add that 0.67 to it. And this is going to give me the approximate value at pi over 4. Let's plug that bad boy in the calculator here. All right, so when I plug that in, I get 3.414. And I'm just truncating here. If you rounded it, you may get slightly different answers here. So that is the approximate value. So what did I find here? I said, okay, I don't have the function, but I'm going to find the estimated value at this point. So I'm going to say it's approximately 3.414. So if you haven't done these before, they take a little bit of time. Do a couple of them. You'll be professional at it. Whoa, that's a big box. There it is right there. That's the estimated value. Does it make sense for this? Let's go check it out. So I'm saying it's roughly 3.414. Yeah, so it's increasing in this interval. It's in between this interval. That seems like a pretty good estimate there. Awesome. Oh, we're crushing it. All right, example 3. What about this? What if I give you a blank table? So now I know R is this function, and I actually gave you the function on this interval, and I don't know the value. So, all right, so we're going to use our calculator to fill in this table and find all these values. Okay, let's head on over to our graph here and check things out here. So we know the function this time, so let's go ahead and graph it, and we want to fill in the table. So make sure that your mode is in polar. Sometimes polars are also called pirate mode. Why is it called pirate mode? Because of all these R's right here. R's. Oh, that's rough. That was really rough. I'm just kidding. It's not called pirate mode. It's only called polar mode. If you're not in the right mode, go to your mode, change it on over to polar instead of function so that we are in polar mode. And let's type that bad boy in there. We got 3 plus 5 sine theta, I believe was our function here we're taking a look at. So we'll go 5 sine theta. And if you want to see the graph, I went ahead and set up my window showing 2 pi, and I kind of went 8, and I set the window here as 6 and 10 if you want to check those out. But that should give me a nice picture of what we're looking at. So we're looking at this bad boy right here. So you can see it coming away and farther from the origin. You know, we were talking about that whole idea of he gets farther away, then he comes back in, then he gets farther away. So we got a lot going on here. So can we go to table? Sure, we can go to table, and it looks like I'm already set up pretty good here. Just make sure when you go to window, second window, that you are either an auto, I don't know why I said that so weird, auto or ask. So if you do auto, it's going to fill it in, and that's kind of nice too. You know, you can say, hey, fill me in a table and just type in maybe like counting by pi over 4. You know, you can type that in, and that'll fill in a table counting by pi over 4. So sometimes that's a nice feature if you want to count by pi over 4s. That's cool. In this case, my table's not as friendly, so let's go back to table set. Let's change it from auto to ask. We're going to ask it specific values. So we're going to go in here, and now we can ask it. We restricted this domain to pi, was our start, to 2 pi. So our very first one, you can just type in pi. It's going to tell you it's 3. Then type in 7 pi over 6, and that'll tell you the next one. Go ahead and fill in the table here. All right, so I got the table filled in there. I hope you got these same decimals here too. And now we can answer these questions. We got a bunch of questions. Let's make sure we're cool. So where is f increasing? So f is just the r equals the f of theta equals this function right here. So where is this function increasing, or where are the values getting bigger? So I can see it's decreasing here in the beginning. It's going from 3 to a half to negative to more negative to more negative to less negative to less negative. So I'm looking at this. See how it's going uphill here? So it looks like from here to here, whoosh, oh, I need a bigger highlighter. Grab that right there. You get the idea. We're looking at something like that. So see how it's always going uphill, so it's always increasing there. So we're going to say it's increasing from what? From 3 pi over 2 to what? So we're talking about the x values or the theta values all the way out to 2 pi. It's going uphill. Awesome. Where is this bad boy decreasing? So if it's going uphill here, I'm going to start. Remember, it was decreasing in the beginning. I think I can just slide this over again. I'm getting pretty lucky. That works out like that. So where is it decreasing? Well, it starts at 3, and it goes downhill, and it keeps going downhill until it hits -2. So it looks like I'm decreasing on this interval here. So we're just looking for where it goes up and down. Awesome. When it does this, ooh, this is interesting here. It says, is there at least one relative extrema on this whole interval from from pi to 2 pi? So I'll get rid of that. On this whole interval, do I have to have a relative extrema, some kind of max or min? Yes, I do. Why? Well, it's decreasing all the way here. It's going downhill to 2, and then what happens? It starts to go uphill. So if it does that, we know what has to happen in there. We have to have one kind of extrema in there. So yes, is there one? Yes, there is at least one. There could be more, but I mean, because we're doing polar functions, we know it's continuous through here. There shouldn't be any bumps if we pick our intervals small enough, but just if there were little bumps in there, some kind of crazy polar function. But yes, there is at least one. Relative, at least one. And why? Well, anytime it changes from increasing to decreasing, and I believe we did this stuff at the beginning of the year, so it changes from what? In this case, it's from decreasing to increasing. So from decrease to increase, that's going to cause a relative extrema there. Awesome, super cool. All right, using the table that we got in there, we filled it in with our calculator. See if you can pause and answer the rest, and then I'm going to talk through them quickly. Good luck. All right, let's start with letter D here. I highlighted it below. Hopefully you said the distance is increasing. Why is that increasing? Well, it's a negative r value. I can see it's negative here over this interval, and it's getting smaller. It's actually decreasing, so I'm getting further away from it, so the distance is increasing. Awesome. So in letter E, you're just looking at this really small interval from pi to 7 pi over 6. It's a positive r that's decreasing, so we're going to say the distance to the pole is decreasing. Hopefully that's just kind of following the rules. Make sure you're cool. Gave you an average rate of change here. How'd you do here? Just make sure you label it. This is some kind of units. I got 1.871 units per radian. Plug and chug into like the little slope formula, and you're good to go there. Kind of mix it up a little bit here. This is a new one. Where are the intervals where the function must be 0? So just kind of checking out to see what's cool. Well, anywhere it changes signs. So if it changes signs, so see how it goes from 0.5 to negative 0.5? So it changed signs here. It's negative, 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 then went back to positive. So we got to cross 0 in this little interval here. So I crossed between 7 pi over 4 and 11 pi over 6. And let's just slide this interval over. There it is right there. I just kind of between those two intervals there. Excellent. Coming on down here to letter H, the big dog. So I wanted you to estimate 5 pi over 3. This time our table actually has it. So we're pretty cool because the table actually has it in there. But we're looking at the interval, the closest one around. So I'm trying to estimate 5 pi over 3. So I picked the closest interval I can. So I'm going to go from here to here. So the closer the better. So I'm going to use that. So that's what I did for my average rate of change. I found 1.87 as the average rate of change in this interval here between these two. And then I use that as the slope of my line between the 2 points. Do a lot of plug and chug, and I ended up getting negative 1.02. So if I compare these two, are they pretty good? Yeah, they're pretty close, man. That's really nice. So we get a good approximation there at that point. So I was a bit overestimating because it's less negative here. The winter one was a little bit more negative. So I kind of was an overestimate there. Awesome. Hey, turns out we can graph this. I just wanted to show you the graph so you didn't think I was just making all this stuff up here. So here's the actual picture. And we were, again, looking only at from pi over 2 to 2 pi. So we're only looking at that one little chunk there. So just so we can see what's going on here, remember this is pi degrees over here. And I'm going from pi to 2 pi. So you can see this is where the function's coming in. And you can see it's decreasing like we said at the beginning. Then it kind of increases all this stuff and comes around like that. But I just want to show you we're only talking about that little chunk there. Man, that is it. Get some good practice in on this. Wrap up the chapter. Good luck on the mesh check. Peace out.